So we were discussing about the basic principle of operation of three-phase induction motor. As I told you, a three-phase induction motor has got a balanced three-phase winding on the stator and a balanced three-phase winding on the rotor. And this is one kind of induction motor where the type of stator and rotor windings are same. Okay, they are distributed three-phase winding on the stator, here also three-phase distributed winding on the stator. Now this type of induction machines are called wound rotor induction machines. Wound rotor induction motor machine, or sometimes they are also called slip ring induction motor. They are known by either of these two terms, because here the rotor terminals are accessible via the slip ring and brass arrangement. And there is another type that is called cage induction motor. I will tell it afterwards. To understand the basic principle of operation, we have taken up this machine. Now, what I was discussing yesterday is that if you apply a balanced three-phase supply on the stator and rotor terminals are kept, suppose, open circuited, then a rotating magnetic field will be produced by the stator. A rotating field will be produced by the stator. The speed, mechanical speed of which is decided by the supply frequency and the number of poles, so much of RPS. And in a particular direction it will rotate in the sequence RYB. So it rotates, suppose, in the clockwise direction. Now this field will also link the rotor coil phase windings, coils. So there will be induced voltage in this winding, in this winding and this winding. So there will be balanced three-phase voltage induced across the rotor terminals, and the frequency of that voltage too will be that of the supply frequency, which you can easily show. However, there cannot be any torque produced so that the machine will start rotating, because for production of torque you require some current to flow in the rotor conductors, and a current carrying conductor placed in a magnetic field experiences a force like that. So this is unable to produce a torque. Now what you do is this: you suppose consider, so rotor will remain stationary and it will be like a transformer. Now what you do, you suppose prior to switching on this supply, prior to switching on the stator supply, you short the rotor terminals by some external switch or wires like this. Keep it shorted. Then we want to study what is going to happen if I apply a balanced three-phase voltage to the stator winding. And the discussion will divide into two parts. That is, rotor terminals should be shorted. Rotor terminals shorted, kept shorted, and initially we will also assume rotor is stationary. Then three-phase supply is given to stator. Now under this condition, so rotor was initially stationary. Even after you have closed the switch, rotor will at t equal to 0 plus will also remain stationary. Although torque may be produced, machine may start. Because of its inertia, it cannot just start to pick up speed like that, because it has got some inertia. So we will consider, so nr equal to 0, at t equal to 0 plus also nr equal to 0. At t equal to 0, switch is closed, suppose. So at that time also rotor is stationary. Let us see whether the rotor conductor will experience any torque to give you any motion. That is what we are going to study. Now, since these rotor terminals are now shorted, there will be induced voltage in each of the phases, and there will be currents flowing in the windings. Okay, and we want to examine whether the conductors will experience a force or not. So to do that, what we will do, so under this condition, suppose this is a single rotor conductor, let us take a single rotor conductor, and the stator field is moving like this, in this direction with a speed ns, and this ns is called synchronous speed, as I told you, and this is in mechanical measurement. And this field, this wave is moving from, suppose, left to right, and let us consider the instant when it is under the center of the, say, north pole. Now we want to find out what will be the polarity of the induced voltage or current in the rotor conductors. This is the rotor, one of the rotor conductors. Let us consider rotor conductor. Now what will happen, this to find out the polarity of this voltage, suppose this positive thing denotes north pole, this is south pole, okay, that is lines of force are coming out here like this. So to find out the polarity of the voltage, it is convenient to keep the flux stationary and assume the rotor is moving in the opposite direction. To ascertain the voltage polarity in a conductor, induced voltage polarity, it is convenient to assume flux to be stationary, field, and conductor to be moving. So whether should I put cross or dot, it is rather difficult with field is moving, because we are familiar with this thing. Suppose this conductor is under north pole, lines of force are moving like this. This situation is equivalent to field is stationary here and conductor is moving in this direction with same velocity, say ns. Are you getting this, to ascertain this polarity? So what will be the polarity of the induced voltage in the conductor? This is the field direction. It will be like this. That is, motion is in this direction. I have to apply right hand rule. So it will come out. It will try to come out here. So what I mean to say, in this one, also I can put dot, just to ascertain this polarity. Now here rotor is stationary and field is moving. Now at this instant, therefore, this conductor is carrying a dot current because rotor is closed on to itself because of your short circuiting the rotor terminals. Therefore the direction of force which will be present in the rotor will be also in this direction. This is the stator field Fs, which moves from left to right. We have switched on, rotor current flows, and rotor conductors too will experience a force in the same direction as that of the stator field. That is important. Therefore, rotor will experience a force in the direction of the rotating field produced by the stator. Therefore, rotor should start moving in the clockwise direction. Stator field is moving like this. Rotor conductors will also start moving in the same direction. Of course, this can be also explained just by Lenz's law without doing these things. That is, theoretically it is like this. See, there are only two possibilities. Rotor may start rotating in the same direction as that of the stator field, or it may rotate in the opposite direction of the stator field. Now, which one will be correct? If I assume that the rotor starts rotating in the opposite direction, then it will violate Lenz's law. Because of what? If it moves in the opposite direction, then the induced voltage will become more and more in the rotor. Is not? Because relative speed between the stator field and the rotor will go on increasing, which cannot be the case. The polarity of the induced voltage in the rotor windings will be such that it will try to oppose the cause. What is the cause? Cause is the relative velocity between the stator field and the rotor. So that it will try to reduce. So rotor must start rotating along the same direction as that of the stator field. Now, still we will consider So at t equal to 0 plus, rotor is stationary. Rotor is stationary. Rotor is stationary at t equal to 0 plus. Rotor is stationary. And it now experiences a force at t equal to 0 plus. At t equal to 0 plus. Rotor experiences a torque, torque or force, whatever you call, torque, along the same direction, as that of the stator field. That direction it will start rotating. Rotor will start rotating. Now, at that condition, let us see what is the induced voltage, etc., in the stator and rotor. So, this condition is called the standstill condition of the machine. Rotor has not yet started rotating, it has just experienced a force. So, at standstill condition, or you can imagine that the rotor is held by hand, not allowed to rotate. Okay, I have kept it like this. Rotor terminals are shorted. It experiences a force, torque, but you are opposing that rotation by some external torque so that it remains stationary. So that situation is called standstill situation. So in that situation, the voltage induced per phase on the stator, voltage induced per phase in stator, let us call that to be E1. The magnitude of that we wrote root 2 pi f phi into kW1 into N1. And in rotor, voltage induced per phase will be equal to root 2 pi. What is the relative speed between the rotor and stator field? Ns, mechanical. So that will be once again Pns by 2 into phi into kW2 N2, where N1, N2 are the respective phase turns of stator and rotor. So this is once again equal to root 2 pi f phi into kW2 N2. And what will be the frequency of the rotor induced voltage? Frequency of rotor induced voltage, or rather E2 of E2, that is E2, will be equal to how much? Pns by 2, because ns is the relative speed. So this is f. So same frequency rotor induced voltage will be there in the rotor, that is same equal to that of the supply frequency. So at standstill condition, your induction motor is just like a transformer whose secondary is shorted. That is primary induced voltage, secondary induced voltage, and the frequency of rotor and stator voltages and currents, they are also of same frequency f. So this is at standstill condition. Now what we want to study is that suppose now rotor starts rotating in the same direction as that of the stator field, and we will assume at any time t, suppose the rotor speed is nr, then what is going to happen here in these equations? So suppose rotor speed is nr rps, mechanical speed. That means I will now draw like this. This is suppose the rotor. stator produces a field Fs. It moves with Ns, RPS, and this is also mechanical, and this is with respect to stationary observer or stator, with respect to stator. And suppose rotor speed is Nr RPS, mechanical, and this is also with respect to a stationary observer. That is with a tachometer, whatever speed you measure. So this is the situation. At any time t, suppose the machine has now started picking up speed. At any time t, suppose the rotor speed is Nr RPS, like this. Then consider the stator induced voltage per phase, E1. Do you think it will change? Stator winding, if you think you are sitting on a stator winding coil, you will see your field is moving past you at a speed Ns. Therefore, induced voltage in the stator is still root 2 pi f phi kW1 N1. But what will happen to the stator induced voltage per phase? It will be, I am writing, you just follow, try to follow how I am writing. Root 2 pi, then the relative speed term will come. Relative speed decides what will be the magnitude of the voltage. What is the relative speed? Ns minus Nr, because these speeds are expressed with respect to same observer. So it will be Ns minus Nr into P by 2 into phi into Kw2 into N2. This will be the induced voltage of that. See, two things should be found out whenever you tell that there is some alternating voltage induced in a coil. You should be interested in two things. What is the magnitude of the voltage and what is its frequency? So what is the frequency of the rotor voltage? Suppose I call that frequency to be Fr. Frequency of the rotor induced voltage will be how much? P by 2 into Ns minus Nr. This will be the induced voltage frequency in the rotor, that is in hertz. And this will be the magnitude. Yes, please. Because Ns is greater than Nr, I have assumed like this, that initially you have energized the stator field. Suppose it is a two-pole machine. Ns value is 3000 RPM, like that it is moving. Now rotor has started moving up, picking up speed. So let us consider that Nr has not crossed yet Ns. I do not know what will happen, that I will see. But suppose at any time t, the rotor speed is Nr, which is less than Ns. It is picking up speed, at least it will start, because it is having mechanical inertia, say 0 RPM, now 1 RPM, 2 RPM, like that it is increasing. Suppose let us assume Nr is less than Ns till now, okay, and we will see it is not possible that Nr to cross Ns, that we will examine. So till now, suppose Nr is less than Ns. So this will be the frequency of this induced voltage. Now one thing you should note here. This one I can write it in this fashion. P Ns by 2 into Ns minus Nr by Ns. Now what is PNS by 2? Stator supply frequency. So this is equal to Ns minus Nr by Ns into supply frequency of the stator, F, that is 50 Hertz. Now you will find often this term Ns minus Nr by Ns will come into various expressions. So this term is given a name called slip, right, S. Because you can do with this Nr as variable, but these things will become clumsy otherwise, Ns minus Nr always. So the relative speed comes into various expressions. For example, in the frequency of the rotor, it comes as S into F. Therefore, what is slip? Slip is defined as, slip is denoted by small s, and it is defined as ns minus nr by ns. That is relative speed between stator field and rotor expressed as a per unit value of the stator field. This ns is constant for a given machine. Ns is constant. This you should remember. And also you can see the induced voltage in the rotor when the rotor is running at nr rps is also given by, as we have seen, root 2 pi into p by 2 ns minus nr into phi into kw2 into n2. So here also what you do, you multiply by ns and divide by ns, like this, the earlier expression that we have written. Here also this can be written as root 2 pi pns by 2 is the supply frequency, and this will be the slip of the machine, slip into phi into kw2 into n2. This is sometimes written as s into root 2 pi f phi kw2 n2. Now, what is this quantity? Root 2 pi f phi kw2 n2 is the voltage induced in the rotor phase when rotor was stationary, is not? That is the first expression. That is here. At standstill condition, what was E2? Root 2 pi f phi kw2 n2. So this one you just not correct means here you write, to be very explicit, you write E2 standstill. Of course, it is under the heading standstill I have written, because once again I am using E2 there. It is under standstill condition. Standstill condition. This you can just modify, that standstill condition, E2 standstill is root 2 pi f phi kw2 n2. Then E2 at any speed nr, when the rotor is running at any speed nr, it is generally denoted by E2 only, and this becomes therefore equal to, in this one I can write it, it will become S into E2 standstill. Let us be elaborate, where E2 is the RMS voltage at any speed nr or at any slip s. So it is often in terms of speed, instead of telling, you can tell in terms of slip, because ns is constant, the speed can be mapped into s. For example, when the rotor is stationary, what is the value of slip? 1. Like that. Okay. When slip is 0.5, it means it is running at a speed of half of the synchronous speed, like that. So we will come to this. So this is the important relationship. The induced voltage and its frequency, they are related by these two things, E2 and this one. Okay. Now, before I go further, we will see now what is going to happen to the rotor speed after you have switched on supply. That you refer to this diagram once again, or you can draw. Suppose rotor terminals are kept shorted and rotor was initially stationary. You have switched on the supply. The moment you switch on, there is a rotating field, stator rotating field Fs, which moves with a speed ns. And rotor experiences force or torque, and it starts moving in the same direction as that of the stator field. And this speed, machine will pick up speed. Let us consider it is a function of time. It goes on increasing. Now two things will happen. As speed goes on increasing, what will happen to the magnitude of the induced voltage in the rotor? It will go on decreasing because relative speed between these two goes on decreasing. Induced voltage magnitude decreases. And the current flowing in the rotor conductors too will go on decreasing because induced voltage is decreased, is not? Therefore, both magnitude of the voltage and the current in the rotor circuit will go on decreasing. That is there. But nonetheless, so long the current is there, there will be torque to accelerate the rotor. So machine will go on further increasing its speed, so long there is positive torque present. So in this way, NR will start increasing. So a time may come when NR will become equal to NS, is not? When the rotor speed will become equal to the stator field speed, NS. At that condition, what will be the rotor induced voltage? 0. And rotor current, of course, will be 0. Therefore, no torque will be developed. And such a situation will occur only when there is no friction present on the machine shaft or windage friction, etc. No friction is assumed. Ideal condition. Stator is supplied. Rotor starts accelerating. Starting from its 0 speed, NR goes on increasing. And when NR becomes equal to NS, machine continues to run at that NS value. And there is no output power, nothing to overcome. So torque developed by the machine is 0. Torque to be overcome is also 0. Therefore, machine will continue to run at that speed NS. Is not? See, a machine, any machine, it is true for any machine. Whether the machine will accelerate or it will decelerate or it will run at a constant speed is decided by two things. One is the electromagnetic torque developed by the machine, motor. In case of motor, electromagnetic torque is the driving torque which is accelerating. Suppose it is moving in this direction. And the opposing torque will be present on the shaft of the machine. As a friction it may come or as a mechanical load. That is the chunk of this. So this is called load torque and it will act in opposition. Your electromagnetic torque must supply this load torque. Therefore, a machine will run at a constant speed if T equal to TL. If at any point of time electromagnetic torque is equal to the load torque or torque to be overcome, then constant speed operation will take place. Constant speed. If TE is greater than TL, I think I will write in a new page. So in general, suppose this is the electromagnetic torque acting in this direction. And load torque present on the shaft of the machine is TL. Then if TE is greater than TL, machine accelerates, motor accelerates. If TE is less than TL, motor decelerates. And if TE is equal to TL, motor runs at a constant speed. Motor runs at fixed speed, at a fixed speed. Therefore, initially, if you assume that I will quickly just do. Suppose this is the machine. These are the rotor terminals. Stationary machine. There is no friction torque, no load torque I have given on the shaft of the machine. You have energized the stator winding. Rotating field results, Fs. There is TL absolutely 0, let us assume. There is no load torque, no friction torque, etc. What is there? Only electromagnetic torque. It will accelerate the machine. What will be its dynamics? T will be equal to J d omega dt, like your P equal to mf. In that equation, speed will go on rising. In the process, the induced voltage and current in the rotor decreases. But so long there is current in the rotor, there will be electromagnetic torque. This T magnitude initially was quite high, but as machine picks up speed, T decreases. But nonetheless, it is always greater than 0. That is TL equal to 0. So machine accelerates. So a time will come when NR will become equal to NS. When it happens like that, then T vanishes, 0, load torque 0, and machine continues to run at NR equal to NS. But what I am trying to tell, let us assume that first there is some load torque present in the form of friction torque. Suppose TL, that is the opposing torque, the machine has to start opposing torque. Opposing torque is suppose T friction only present on the shaft. Okay, friction torque present on the shaft is machine prior to you switch on the supply to the stator. You switch on the supply. Now there is a condition. There is electromagnetic torque developed by the machine. But it must be greater than T friction, which obviously will be certainly higher. Otherwise machine will not start. Are you getting? If suppose your machine gets jammed because of not using it for a long time, even if you give supply, machine may not start because friction to overcome is pretty high. Your bearing friction, etc., has increased tremendously. But anyway, let us assume some small friction torque is present. Then machine will start running because T is greater than T friction. It will go on running. So what will be the final fate of the machine now? Its speed will go on rising. But will it go up to synchronous speed now, NR? It will at some speed, NR will attain some speed such that there will be induced voltage in the rotor, sufficient induced current will be there in the rotor, such that the electromagnetic torque developed by the machine will just match T friction. A time will come. And it is at that time machine will run at that constant speed. Like that it will go. Now if you assume, suppose are you getting the point? No. So induction machine speed will be perhaps close to synchronous speed, but just below it. By what amount it will be below NS? That will be decided by how much torque it has to overcome. If you have increased the load torque, suppose mechanical load torque you have pushed further, suppose it is running at some speed less than synchronous speed. Now further I have imposed additional load torque on the shaft of the machine. Then immediately rotor speed cannot change. Getting? Suppose initially now, therefore suppose the machine is running such that electromagnetic torque developed is equal to T friction, and the speed of the machine is suppose some NR0 initial speed, which will be of course less than NS, that I know. It is running steadily at this NRO RPM, no load speed. Now suppose you imagine on the shaft of the machine I have imposed additional load torque. Okay. So now on the shaft, additional load torque is imposed. Remember, speed cannot change instantaneously because of inertia. Speed cannot change instantaneously due to inertia. So tell me what will happen to the electromagnetic torque at T equal to 0 plus. Suppose at T equal to 0 you have put additional torque to overcome. What will happen to the electromagnetic torque? It cannot change instantaneously because electromagnetic torque depends on what? Upon the relative speed between these two, which has not changed at t equal to 0 plus. Rotor current, has it changed? No, at t equal to 0 plus it has not. Electromagnetic torque will depend upon phi and I, that has not changed. So electromagnetic torque at t equal to 0 plus remains what it was here, equal to your frictional torque earlier, T0 at initially when it was supplying only frictional torque, T0 was equal to T friction. At this time, at t equal to 0, suppose you have put extra load at t equal to 0, and at t equal to 0 plus, right after that, value of t is how much? T remains T0 at that time. But load torque, earlier it was equal to T friction, now I have increased to some value. I have imposed additional load torque. So at that time, rotor will do what? Rotor will decelerate, because electromagnetic torque developed by the machine at t equal to 0 plus is less than the load torque. So machine cannot but decelerate, because load torque is more. And what will be the final operating point? On what basis will it be decided now? Now speed starts falling. Rotor currents will become more because induced voltage more. Electromagnetic torque developed by the machine will become more. So it will settle to that speed, which will once again develop an electromagnetic torque, which will become equal to your new load torque. So as you go on increasing the load torque on the machine, new steady operating point will be obtained automatically. Machine will adjust itself in such a way that it will try to match the load torque present on the shaft of the machine. But in the process, its speed will fall gradually, starting from its initial NRO value. Are you getting? So this is how things will go on. Therefore, at least this thing let us tell that, you know, it is the relative speed which determines the performance of the machine, induction machine. So the concept of slip is important, because slip is this one ns minus nr by ns. Are you getting? So you remember an induction motor, the value of range of slip value for motor operation of an induction motor, for motor operation, is between 0 to 1. Remember, A is equal to 1 corresponds to standstill condition always. A is equal to 1 means stationary, machine is stationary, NR is 0. A is equal to 1 corresponds to NR equal to 0, hence standstill condition, standstill. And A is equal to 0 corresponds to NR equal to NS. And it is the absolute no load condition, you can say. See, T friction is always present, you can't do. You imagine that friction also I have made it 0, then only it will run at NS, but certainly not beyond that. So, the slip NR equal to NS is, we can say, absolute no load condition. Absolute no load condition. So this thing, that is NR equal to 0, this one this way, you can always remember. And also this equation is often used, that is A is equal to NS minus NR by NS. This is often used. It is same as this one. NR, you have to, suppose slip value is given, you will be interested to know what is the rotor speed. Use this formula. For example, just consider, suppose a 4-pole machine. Example, 4-pole machine. supply frequency is 50 hertz. And the slip, it is given like the motor runs at a 4% slip. What is the speed of the machine? So what you will do? First you will write NS is how much? 1500 RPM. This should come automatically. 4-pole supply frequency, this one, NS is 1500 RPM. All mechanical thing I am doing. Of course, slip you can calculate with respect to electrical thing, but then both of them should be electrical, like that. Ratio remains same. So NS is 1500 RPM. And what is the value of slip? 4% slip means 0.04. See, slip is a percentage slip is nothing, is defined as NS minus NR by NS into 100. So actual slip, per unit slip is this one. This is per unit slip. So it will be 0.04. And your NR value should be 1 minus 0.04 into 1500. So much RPM. So that is 0.96 into whatever it comes. So much RPM. How much? 1440 RPM. Huh? I mean, something will come, 1400. Okay. So this will be the RPM. This is how you will calculate slip. Therefore, if you know, see, this is important, the number of poles, supply frequency, and 4% slip of the machine, you can say. On the other hand, if the rotor speed is given, if you know the synchronous speed, then also you can calculate slip. So instead of telling machine is running at this RPM, that RPM, often it is said that slip is this much, that much, like that, how the machine will be operating. Now I will tell you about the what happens, like about the equivalent circuit, whether some equivalent circuit we can make out of this one. Whether we can find out. This you try to listen carefully. See, we will assume, we will not go into that ideal induction motor like that. That we can also do, like transformer we did. But what I will try to tell, you try to first get the feeling what I will be doing. Actually, I will borrow all the results from transformers and nicely put it here. But before that, I must tell you something why I can do here like that. Suppose these are the rotor terminals. Okay. And these have been closed. As I told you, at least during starting condition, when the rotor is stationary, it is just like a transformer. You have given a voltage, some voltage is induced here. And not only that, at standstill, frequency of these two sides are same. So at least equivalent circuit of this induction motor at standstill condition should be similar to that of a transformer. Ratio of induced voltage is ratio of effective number of turns, of course here, and the frequency is same. But you may be at difficulty if I say when the machine is running with some speed NR, it is exactly not like a transformer. Because of what? Because the frequency of current in the stator is F and frequency of current in the rotor is different. S into F. So it is not like a transformer now. Primary and secondaries are carrying current whose frequencies are different. How really you can then find out equivalent circuit in the same way as that of a transformer. Now this point I want to highlight why you can do like that. This I will do in this way. Suppose you imagine that the rotor terminals are open you don't write anything, just listen. Suppose you just imagine rotor terminals are opened. You have given stator supply. Then what happens? A field is produced which moves with a speed ns by the stator. Rotor terminals are opened. And let us also assume this windings has got no resistance per phase and no leakage flux is there between stator and rotor. All those assumptions. Okay. Then this voltage whatever I have applied line to line and per phase voltage whatever I will calculate here. Are you getting? What will be the induced voltage? Per phase, this should be equal on the stator side, whose value should be root 2 pi f phi into kW1 N1. You getting? Like transformer, your supply, the KVL loop in this one. Applied voltage is this much, induced voltage, they must balance their magnitude, just like a transformer. KVL is to be satisfied. Therefore, for a given voltage, just like transformer, and given frequency, kWn1 is constant of the machine, your flux level in the machine gets decided. The flux per pole in the machine gets fixed. That is, what will be the strength of the field gets fixed by this flux level. No, flux level is this B, this area, etc. It gets fixed just like a transformer. Therefore, once again, if I will argue like this, no matter what you do, whether you keep secondary open, closed, this, that, whatever you do, the flux level in the air gap of the machine, that should remain what it was earlier. That is, when it was opened, like secondary is loaded like that. But as you know, if you close this one, so what will be the current drawn at this stage? Some current will be drawn, three-phase balanced current will be drawn by the machine, and that current should produce a B distribution whose flux per pole is this one, that is there. But that current, by what name should I call it? Magnetizing current. Suppose let us neglect those cold loss, hysteresis loss, etc. Only magnetizing finite current it will take, and that may be vanishingly small if it is very ideal induction motor like that. But since we know transformer a bit, let us start from that point, that it will take some magnetizing current balanced three phase, and it produces this flux per pole in the machine. Now, what I am trying to tell, if I close the secondary winding, there will be secondary winding current. Therefore, air gap flux should be what it was earlier. But how it can be? Now rotor carries current. Rotor windings too will produce some field. Is not? Will it be a rotating magnetic field? Rotor? It will be, because rotor induced voltage are balanced three phase. It is closed by itself. So balanced three phase current will flow in the rotor windings. So rotor too will produce a rotating magnetic field. But your condition is that your flux per pole should remain same. That is, after you have closed this, the flux pattern in the air gap should be same as it was prior to closing of this rotor terminal switch. So how it can compensate for that? So stator will draw additional current now from the supply, and will try to nullify the effect of the rotor flux per pole, rotor field produced by the rotor. Are you getting? Now consider, say, NR equal to 0, standstill condition. So now we are having this thing. There is some stator field because of magnetizing current. Its speed is ns. At NR equal to 0, standstill condition, rotor speed is 0, NR equal to 0, rotor speed. But rotor has supply frequency current flowing in the rotor winding now at S equal to 1, because SF is the frequency of rotor current. S is 1 during standstill. So rotor carries balanced three-phase current. What will be the speed of the field produced by the rotor? F, that is ns. in mechanical speed will be ns in the same direction. Okay, and it will rotate in the same direction. Therefore, the stator will draw additional current and can compensate this one. Anyway, today time is up, so tomorrow I will discuss.